Okay, now this next topic, this heading is promising a bit more than it can deliver, actually. We're not going to learn how to differentiate all rational functions or fractions. A rational function is just a fraction. If you're differentiating fractions, of course, you can differentiate any fraction at all, something over something, by using the quotient rule. There is no quotient rule for integration. There is no chain rule. There is no product rule for integration. Lots and lots of special rules we have to use. So some fractions can be integrated because we can recognize if we've got an f dashed of x over f of x, in other words, a fraction that when you differentiate the bottom you get the top, then we know that a log differentiates to that. And remember, when you integrate and the answer's a log, you put these annoying modulus signs in, and sometimes if you forget them, it doesn't matter. So forgetting them is not a terrible thing to do. Okay? Our job for some fractions is to think, does this fraction look like the top is the derivative of the bottom? Okay, and if it does, then the answer is going to be a log. So here's our first one. So part A, is the top the derivative of the bottom? Well, no, because the derivative of the bottom I'd have to have all over 2x plus 3. In order for this to be a log, I'd have to have a 2 on the top, because that's the derivative of the bottom. So I've written down an integral I can do, but at the moment this is completely useless because it's not the same as the question I'm doing. So I've got to actually answer this question. So what's the point in writing this down? Well, it's actually very similar. It's just that instead of a 5 on the top, I've got a 2 on the top. But I'm not allowed to make up my own question completely. In fact, I've got to turn this somehow back into that. So I can't change the question I was asked, but I can put a fraction in front of my answer to make it equal what I was asked. So I've got a 2, which I have no right to have. So I'll get rid of it again. By dividing by 2, remember a constant outside the integral, we can shift constants outside the integral without penalty. Can't shift x's outside, but I can shift constants outside. And this 5 that I'm supposed to have, I can put a 5 over 2 on the top. So 2 cancels this 2, and the 5 provides that 5. And because this is a constant, it's allowed to be pushed outside the integral. So I've now got a constant times an integral I can do. So this is good times. All right, I've got 5 over 2 times. This is an f of x on the bottom, it's f dashed on the top, so I can use the log rule. The answer is log of the bottom, or modulus of the bottom, log of modulus of the bottom, and I mustn't forget my plus c. So I've done the first one. So as long as you recognise them, set up an integral you can do, and put the correct fiddle factor in front, then log integral. So easy. So let's use that method for this one. So for part B, is the top the derivative of the bottom? No, it's not. In fact, this fraction I'm going to have to split up, aren't I? So this x plus 1 over x squared, this should remind you of core 2. In core 2, you'd have done something like x over x squared plus 1 over x squared, and you'd have got x to the power minus 1 plus x to the power minus 2, and then you'd have differentiated these using the power rule. So x to the power minus 2, we could integrate using the power rule, but if we're integrating x to the power minus 1, if you try and use the power rule, add 1 to the power, you get 0. And you can't divide by 0, so the rule for integrating powers does not work for x to the power minus 1. In fact, x over x squared, rather than go to x to the power minus 1, I'm going to choose to do that part as just 1 over x. X over x squared and x cancels, so it's 1 over x. And then the other one I am going to have plus x to the power minus 2, and I'm going to have my dx. And I recognise 1 over x. The top is the derivative of the bottom, so the answer is, so the integral is log of modulus of the bottom. Okay, and then the other one, add 1 to the power, minus 2, add 1 to it, you get minus 1, divide by the new power, so that's 1 over minus 1, so it's going to be minus 1 lot of x to the power minus 1, and plus c, and that is my answer. Okay, and if you forget those modular signs, then normally you won't get into trouble. Okay, so 1 over x integrates to log x, okay? Don't be fooled into thinking that you know what log x integrates to. Integrating log x is tricky. We don't know how to do it yet, and that comes up later, all right? So you've got to be going the right way around. You need to start with 1 over x for it to turn into log x when you integrate. Okay, and this one here, back to the first type, okay? If I look at the bottom, 1, if I try differentiating the bottom of my fraction, 1 will differentiate to nothing, and sine 2x will differentiate not quite to cos 2x, but something like it. So that's what I'm going to do. I'm going to set up an integral I can do. 1 plus sine of 2x dx. So we think, what would we like to have on the top? Well, 1 plus sine 2x differentiates to, it's going to have cos 2x in it. I'm differentiating, so sine differentiates to plus cos, but there's a 2 in front of the x, so a 2 pops out. So that's the integral I can do. This is going to be a log. Is it the same as the integral I was given? No, I've put a 2 in that I've got no right to have. So I've got to get rid of that 2 again, so I need an over 2. There wasn't another constant there, so I just need a half. So my fiddle factor is a half, and this is the same question as I started with once I put my limits on. But it's now got the advantage of being an integral that I can do. So I recognise, because the top's the derivative of the bottom, that I'm going to get log of the modulus of the bottom. Okay, that half just sits there. So 1 plus sine 2x is inside my modulus, and then I've got to do squaredy brackets and bang my limits on, 0 and pi by 6, and I've got to put the limits on. So when I put pi by 6 in, I'm going to get half of log of the modulus of 1 plus sine of 2 lots of pi by 6 is pi by 3. Okay, so that's 2 sets of round brackets minus each other. And for the lower limit, I'm going to do a half of log of brackets 1 plus sine of 0. Okay, modulus of sine plus 0. But in fact, the modulus signs I've missed off some brackets. I've turned the modulus signs into brackets. So I said you could be sloppy. Here, these things are both positive anyway, so the modulus sign would have had no effect. So being sloppy with your modulus signs, I think I've said it before, is normally not a huge penalty. Right, so sine of pi by 3, your calculator will tell you, it's root 3 over 2. So you're going to have a half log of 1 plus root 3 over 2 from this, minus a half log of 1 plus sine 0 is 1. So it's minus a half log of 1. Sine of 0 is 0. So you might be tempted to leave your answer like this. If you're a smart aleck, you might be tempted to actually say, oh, I know how to do a log minus a log. It's log of that one over that one. And then I'd be dividing by 1, so it would have no effect. What's going on? Well, log of 1 is 0, you see. So graph of e goes through 1. Graph of log goes through 1, 0. So y equals log x, we can see that log of 1 is 0. So rather than use your calculator, it's good if you can spot that's going to be 0. So the answer is just a half log of 1 plus root 3 over 2, which is positive, so no modulus signs needed. And that's a nice exact answer. You can get it as a decimal if you want to, but more often than not, you'll be wanting to leave your answers as beautiful, exact things. So, integrating when the answer is a log, okay, set it up so the top is the derivative of the bottom, okay, and then put whatever you need to in front of that integral to turn it back into the question you were asked. And then it should be straightforward like these ones. Good luck.